This colloquium will be given by James Sprittles. He is a professor at the Mathematics Institute at University of Warwick, and he is generally interested in computational modeling of small-scale flows, with his more recent research being focused on influence of gas kinetics and thermal fluctuations on droplet dynamics, with focus on some applications around multi-material 3D printing and thermal management. So we have 34 participants. Over to you, James.
Okay, so as Sepide mentioned, I'm interested in the dynamics of droplets, and I guess many of you are aware of the applications of this kind of research, but I thought I'd just start by mentioning a couple which I've been involved with and which I'm interested in. So some of our research was in collaboration with MIT and Bell Labs, and they're interested in thermal management. And so the effect which they discovered was that when you coat surfaces with non-wettable surface, you can induce jumping through coalescence, and that can remove heat from surfaces. So let me show you how that works. So typically on a normal surface, you see big drops forming and being pulled off by gravity. But on this special coatings, you can see drops of a much smaller size being removed. And that's because they coalesce with a neighbor and can jump from these surfaces. So that's an area where we did some modeling. As Sepide mentioned, there's a project with Nottingham on 3D printing, but 3D printing of molten metal droplets. So the attempt to kind of make a metal jet 3D printer. And the interesting thing there is, unlike usual 3D printing, if you like, which is fully commercialized, here there are a huge number of challenges which are yet to be overcome, such as, for example, you can see the bonding between these droplets is extremely poor. And as a result, although I can show you what looks like a wonderfully 3D printed object, in reality, if you start prodding this, it will break very easily. Then another area I've been interested in is spray cooling, and in particular, looking at the dynamics of single drops impacting hot surfaces. So the hope is that you can remove heat from these surfaces through evaporation, but the enemy here is the Leidenfrost effect. This is something I'll describe a bit later in some detail, but essentially these droplets fail to actually contact the surface due to a vapor layer. And the result is, if you look at the thermal imaging, that essentially these drops remain at the same temperature, the surface remains hot, and you can't remove heat in the way you hope you might. Okay, so these are some applications. What I'm going to be concerned with today is really the fundamentals of these kinds of processes. So to give you an overview, the kind of droplet events I'm going to be looking at are the impact of liquid droplets on solid surfaces, the impact of droplets with each other, and the wetting of surfaces by droplets. So once they've contacted, how they spread out and whether there is any complex dynamics occurring. So the questions you're typically interested in here are whether these drops are going to bounce off each other or off the surface, or whether they're going to merge. And in wetting, typically you want to know how fast these liquids can spread across solids. And if they go too fast, how they generate things like splashes. Now, the thing that kind of draws these three problems together is the presence of very thin layers of gas, so gas nanofilms. And that's what a lot of the talk is going to be about, trying to understand how to model these and what kind of physics is involved. The final thing I'm going to talk about today will be the Leidenfrost effect. So this is the levitation of drops on their own vapor. This is slightly different because we have heat transfer here, and we also have much thicker films in general. So for a start, our focus is going to be in these three phenomena. And let me just start by addressing the rather simple question of why the air matters. So the kind of prevailing view maybe 20 or 30 years ago was that the air shouldn't matter. And you can kind of convince yourself of this relatively easily. If you look at a droplet of water even, which is relatively low viscosity, it still has a much larger viscosity than air. Its density is much larger than air. So you could easily convince yourself that the dynamics of the gas, or air in particular, won't have any influence on droplet dynamics. And if this is your kind of belief, then certainly if you change the air pressure or you change the gas surrounding this, then that shouldn't alter the drops dynamics either. So to give you an outline of what I'm going to talk about today, first of all, I'm going to kind of break this view and show you why the gas certainly does matter. Then I'm going to explain why these kind of seemingly innocuous problems, which are very much on the macro scale, so we have a millimeter sized drops, why they require complex nanoscale physics to be understood. And then I'm going to develop a computational model which describes experiments and hopefully gives some new insight into these problems. Okay, so starting off with experiments. So some of the early evidence for the influence of the gas on droplets is from the discovery essentially of these very small gas bubbles which are found underneath impacting drops. So this goes back to 91. And if you look in this paper by Chandra and Avadisian, they actually say that this could be two different possibilities. Firstly, the impact causes some cavitation to create a bubble, or secondly, the kind of correct explanation, which is that the droplet deforms underneath due to the layer of gas acting as a kind of cushion, and as a result, a droplet is entrapped. And there are follow-up articles which begin to explain this phenomenon more clearly. Now, in drop-drop collisions, the effect was well recognized in the 90s, and I'm sure probably before. What's really interesting there is if we look at kind of head-on collisions for simplicity, if these droplets impact each other slowly, then they merge. If we speed up a little further, they bounce off each other. And the remarkable thing is if we speed up even further, then they merge again. So there is two transitions between merging and bouncing to merging for any kind of theory to try to predict. And what's interesting and shows the real importance of the gas is that if you change the ambient gas pressure, so you increase the atmospheric pressure, then you move these boundaries between bouncing and merging. So you change the impact speeds at which this occurs. So perhaps the most famous example showing the relevance of the gas is these famous article by Sid Nagel and colleagues in Chicago. And what they did is they put the drop impact problem inside a vacuum chamber and looked at what happens if you reduce the gas pressure. And probably many of us have seen this before, but at the time it was kind of remarkable. And what you'll see is that at this reduced pressure, you see no splashing at all, whereas at higher pressures, at ambient pressures, you see splashing. So clearly the gas isn't some kind of secondary importance here. It's very much the key effect which dictates whether drops splash or not. So there's this nice quote which I put in from the group, which says that a drop which splashes in Chicago wouldn't necessarily at the top of Everest where the pressure is less. Okay, so this discovery stimulated a huge amount of research in the subsequent years. And the real question was, well, how does the gas influence the drop? And the first possibility was that as a drop comes down, there is a gas layer trapped underneath it, and somehow that changes the characteristics of the splash. So there are nanofilms before contact which affect the splash. The second possibility is this drop touches down, there's a thin bubble caught here, but that it's actually the spreading process that is important for splashing. So there are gas films in front of this moving contact line which dictate whether a splash occurs or not. So the subsequent work was all about trying to look at these gas and nanofilms and measure them. So people developed new techniques, started looking underneath the substrates at these impacting drops and measuring the gas films which were formed using things like interferometry. So in 2011, 2012, there were a host of papers, one by Nagel's group, showing that the splashing in this particular impact occurs a long way away from the bubble, which you can see is just trapped in the center here. Then there were articles looking at measuring the size of the entrapped bubbles. there were articles looking at the touchdown, the first contact, how it occurs, how it depends on properties. As a result of all this, there was this kind of remarkable discovery, which I will show you in video form here. So here you will see two drops bouncing off surfaces, and these surfaces have remarkably different properties. Now, usually I'd open this to the floor to ask you what you think the difference is between these two solids, but you can just think in your own mind what you think, how you think they differ. So typically someone always mentions the idea that there's superhydrophobicity. So this is a very rough, non-wettable surface, and that's the drop impact on the left. So this drop actually touches the surface, but because the surface is non-wettable, it rebounds. In contrast, on the right, we see this new discovery in 2014 that very smooth surfaces can have air films under the drop which cause them to rebound. So this is actually a wettable surface. The drop would spread out on it when it contacts it. So I think it's kind of remarkable that a typical surface, a drop will impact and spread on, but at either end of the scale, very rough or very smooth surfaces, you can create this bouncing phenomenon. So going into a little bit more detail, we'll look at the experiments by Kolinsky in 2014. And this is a typical, well, this is one of the experiments from the article. And what you'll see is the impact here and the measurement of the gas film being captured underneath. And I think darker here is lower areas of lower film height. So this is a case where the drop never touches down. You have measurements of all the film profile, and you'll see rebound in this case. So very similar to drop-drop collisions, what we see here is that when we have sufficiently high speeds, we will see this drop contact the surface and wet as usual. And obviously we want to try to understand how to predict that speed at which wetting occurs. What's interesting is that there are two articles on this within a year of each other. The Kolinsky article predicts that the film heights are around a nanometer or two before contact. The De Ruyter says a couple of 100 nanometers, and something we'll do later is look to clear up this discrepancy. Okay, so moving on to theory, what are the physical mechanisms? How can we develop mathematical models for these kinds of problems? So what's broadly accepted in these problems is that you can describe the gas using viscous lubrication theory. So these films are very long and very thin, and so lubrication theory typically does a good job of describing them. What's also recognized is that if we write down the usual kind of incompressible inertialist formulation, the one we kind of derive as undergraduates, then the gas is characterized entirely by its viscosity. The viscosity is pressure independent of the ambient pressure. And so this usual formulation can't describe these experiments we've seen. So there was a whole kind of host of articles looking at what to add to this formulation to account for this dependence on ambient pressure. So people have suggested that inertia is important, and certainly it will be in some cases. That compressibility is what adds the effect, evaporative cooling, or Kelvin-Helmholtz instability. So these are just a few of the articles on this that I mentioned. So what I'm going to look at today, which is certainly the primary effect in some regimes, is the idea that gas kinetic or rarefied effects in the gas are what needs to be accounted for. And a number of people have suggested this and even worked on it in drop-drop collisions. In particular, there's a very nice article by Ji Li I'll talk about in a minute. In drop solid before contact, there are articles on high-speed wetting, coating processes, and on post-contact wetting, which I'll talk about a bit later. So to give you a picture of how rarefied gas effects or gas kinetic effects manifest themselves, what I'll do is just consider a simple case where we have some channel. You can think of this as being the film between the drop and the solid, if you like. And let's just think about the solid moving at some speed. Then typically within one mean free path of the solid, so this is around 100 nanometers for air atmospheric pressure, we have a region called the Knudsen layer where we have strongly non-equilibrium flow and the Navier-Stokes equations don't apply. So to describe this region, we need the Boltzmann equation. So what the flow profile might look like is something like this. And we have this boundary layer of non-equilibrium flow. And this is all characterized by the Knudsen number, which will be the mean free path divided by the height of this film. Now, when the Knudsen number is much less than 1, we're in a really nice slip regime. Everything is very simple. And we can just attribute all of this nastiness to a boundary condition, which says that there is a jump in velocity at the boundary. So we no longer have no slip. And that is generated by the shear stress acting on this interface with a slip length, which is just the mean free path in the gas. So what we start to see now, finally, is somewhere in our model, we have a link between the gas pressure and the model. And that's because the mean free path is inversely proportional to the gas pressure. So as we reduce the ambient pressure, as they do in experiments, we increase the mean free path, and that means essentially more slip between the gas and the solid. Okay, so that gives us a qualitative picture of what's going on. The problem, or kind of the interesting thing, if you like, is that in the experiments, for example, on drop impact, we see film heights that are 100 nanometers or less. And given that the mean free path in air is around that size, the Knudsen number is actually of the order of 1 or even larger. And so these slip models, which are mathematically rather simple, will fail. And what we really need to do is describe this thin gas layer using the Boltzmann equation. What I want to kind of convince you today is that when we have lubrication framework, this is actually a relatively simple thing to do. And it's only when we go outside the lubrication regime that things become a lot more difficult. Okay, so starting with drop-drop collisions, where some previous work has been done, there's a very nice article by Li in PRL in 2016. And what he does is he incorporates gas kinetic effects into drop-drop collisions that are head-on so that he can consider axisymmetric, and he uses finite elements. So this shows the experiments of Panlaw and Zhu with Li's simulations overlaid. So the black lines are his, and you can see this kind of perfect agreement. Now, what I'm going to kind of hammer home or bang on about throughout this talk is that to predict these shapes is relatively easy. What is hard is to predict the transitions between merging and bouncing. But Li manages this, and the reason he manages it is he captures these thin gas layers in between the drops using gas kinetic models. So Liu and Botha then in 2019 tried to extend these ideas towards 3D using volume of fluid, and essentially struggled to do that because of this hugely multi-scale problem which they encounter. So what they do is they say, well, we're not going to describe the dynamics of the gas film so much. We're just going to prescribe whether the drops bounce or whether they merge. And what you can see here is that if they prescribe bouncing for an experiment which bounces, everything looks great. If they prescribe merging for an experiment which merges, everything looks great. So as I said it before, the challenge really is to predict the transition. So the challenges we're left with, firstly, these are for drop-drop collisions, and we might be interested in drop solid dynamics, which I'm going to talk about now. And secondly, we have this huge multi-scale challenge in that the drops can be on the millimeter scale and the film dynamics are on the nanoscale. And what we don't want to really have to do is capture these kind of million orders of magnitude in 6 orders of magnitude, 10 to the 6 in length scale directly. So the first article I'm going to talk about, the lead author was Mikita Chabinsky, and this is going to be on why drops bounce off solids. So throughout this framework, which I'm going to build up, the liquid is perfectly well described by the Navier-Stokes equations. Everything in there is macroscopic. And as we know, the Navier-Stokes equations are going to require information from the gas on basically its pressure and its stress. So what we're going to try and build up is a lubrication model which gives us these information. So just from a mass balance, we see that as we squeeze this film, so the height decreases, there must be a corresponding mass flow rate out, which is given by this phi. And so this is the balance we have. Now, what we can look at is an auxiliary problem of flow in a channel to understand how this mass flow rate is driven. So there are two components which we're all well aware of. Firstly, the liquid itself could drive a flow in the gas through Couette flow. And secondly, if there are pressure gradients, then we can drive a Poiseuille flow. Okay, and it's the addition of these two flow rates which gives us our total mass flow rate. So if we just had Stokes flow, we can immediately write down what all of these expressions for the mass flow rate of the Couette component, the shear stress of the Couette component, etc., what they all are. The 2 pi r's here are just because we're in axisymmetric coordinates, and we see things we recognize like pressure gradients, 1/12 mu, all these kinds of things. As I mentioned before, the problem is that we don't want Stokes flow. What we want are solutions to the Boltzmann equation. And for simplicity, I'm going to start thinking about diffuse reflection from both the solid and the liquid. So that means essentially particles come into these and are ejected with equal probability in all directions, unlike specular reflection where particles come in and then rebound off like it was like a tennis ball on a wall, essentially. Okay, so in this case, what's nice is there's been a huge amount of work done on solutions to the Boltzmann equation in channels, typically in solid state type devices. And what we're going to do is essentially steal all that information and apply it to fluid mechanics. So what is known there is that you can take the Boltzmann equation, you can find these Couette and Poiseuille components within the linearized Boltzmann solutions, and you can modify these expressions to account for the fact you're solving the Boltzmann equation simply using flow coefficients. So these flow coefficients are going to be depending on the Knudsen number, which we remember is essentially the mean free path divided by the height of the channel. So all we need now are these flow coefficients as a function of Knudsen number, and we have everything we need to essentially describe Boltzmann type flow in these channels. So to do that, before I do that, let me explain a kind of nice way of picturing how things are going to work. So as I said before, the actual gas viscosity doesn't depend on pressure, it's a constant. But we can define an effective viscosity, which is simply the actual one divided by this flow coefficient. And that will then give us a picture of what's going on. So if we look at this effective viscosity at small, the way it's kind of set up, at small Knudsen numbers, we have the usual viscosity of air. But as the Knudsen number increases, this effective viscosity reduces very quickly. So essentially what that means is that at higher Knudsen number, it's relatively easier to remove gas from channels than it would be with the kind of no slip Stokes flow type model. So similarly with the shear stress, we can again see an effective viscosity, which is the actual viscosity divided by the flow coefficient. And we have a second curve that looks like this. So here we've just taken the values from the Boltzmann equation, which are the dots. We've fitted a line through them. There are a number of other possibilities we could have approached. Semi-analytic models based on variational type methods are what I used originally. But given that this is just a function of one variable, it just seems silly to do anything more complicated than just fit a curve through it. Okay, so what does the model actually look like? So we have the usual Navier-Stokes equations in the liquid, and then essentially all this gas dynamics manifests itself through the boundary conditions acting along this surface. So it's axisymmetric, so everything is just a function of the radial coordinate and time. We have a second order PDE for the gas pressure. We have an expression for the shear stress. And we have these coefficients in terms of various things that we know. Okay. On top of this, to force these surfaces to touch each other at very thin, when the gaps are very thin, reach the kind of scales of tens of nanometers, we have disjoining pressure, which we have to add. It seems a little bit ad hoc at this point. It looks like all it's going to do is just touch the two surfaces. But what I'll show you later is it actually brings its own kind of physical effects with it, which we can measure. So the nice thing about this model, which alleviates this horrible multi-scale challenge, is that we only mesh the liquid domain. So Ji Li, for example, had developed these amazing adaptive finite elements for both the drop and the film, which had to capture all these scales from nano up to millimeter. What we have is just simply a drop with some finite elements, and the gas dynamics comes in through the free surface boundary conditions. So let me show you a typical simulation of two drops colliding. This will be the normal view, and then here I'm going to zoom in on the film between them. You see it's got an aspect ratio 1/300, so I can capture what's going on in between the drops. Okay, so what you see in this case is the drops aren't actually going to touch each other, and as a result they will rebound off each other. Okay, and similar to what I showed you, what Ji Li has managed, we benchmarked against both his work and experiments that he benchmarked against, and we can see the collision very well reproduced. So what about drops bouncing? What about the new stuff for drop impact on solids? So this is our simulation compared to experiment, which is just the film, and a close-up of our simulation here. And you can see that qualitatively things certainly look right, and this is a case where the drop rebounds off the solid. So this is the heat map. I'll explain how it works in a minute for the film heights as a function of time and space. And this is our simulation. And so you see the agreement looks pretty good. What's nice is that we can pick out some of the finer features in the experiment. So this shows the film heights as a function of radius. Notice that it's 0.5 micron by 1,000. So although it might look sharp here, it's actually very much smooth. What we see here, so this would be curve 4 here. There's a single minima here. That corresponds to blue, a height of around 100 nanometers at this time. Later on, what we see is the development of a second kink, a kind of second minima here, and that's curve 8, where you see a local minima, well, global minima here and a local minima here. So the experiment shows that as you go above 0.75 meters per second, you transition from bouncing to wetting these surfaces. If we run this model without all the gas kinetic effects, then the model predicts 2 meters per second, so miles away from the actual correct value. If we put in the gas kinetic effects as described with nothing to fit, then we get 0.74 meters per second. Okay, so let me show you, this is the minimum film height as a function of time. So when this goes to 0, there is contact. You see at 0.73 meters per second, the drop never actually contacts the surface and rebounds. At 0.74, it comes along and eventually contacts. Now you can see here that we can predict what the kind of film height, the characteristic film height is before contact. It looks like about 20 or 30 nanometers. What's interesting is Kalinsky said 2 nanometers, De Ruyter said 200 nanometers, and it looks like the truth is actually between these two experimental measurements. So just to summarize, this is the drop bouncing phenomenon I showed you earlier. So it's water glycerol mixture 10 times more viscous than water. The experimental transition is 0.74, conventional model 2, and our new model is 0.73. What's nice is that we can now make new predictions. So we can essentially do kind of virtual experiments with our simulations. And the virtual experiment we did was to think about what happens if we put this experiment in a vacuum chamber, which had never been done before. So this now shows what happens when you lower the ambient gas pressure, how the transition between bouncing and wetting changes. So up here you see the classical model miles away from the reality. What's interesting is down here we see a new low speed transition. Now they see this in the experiments because these drops, they come down and they bounce, 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 and then they suddenly wet, and that is the low speed transition down here. And what's also interesting is we see very clearly two different modes of contact. So the first mode, the kind of most common mode we see, is this red dots here, red triangles here. And what happens there is a film forms, and on that film waves grow due to the van der Waals forces, and they eventually contact the solid. But there's also a second mode, which you see down here in blue, and that's when it's an edge-driven contact. So this kink at the front touches down. And you can see the transition between these two at reduced pressures here. So what's really nice is that a month ago, there was a paper published in the Physics of Fluids aimed at trying to get at these predictions that we'd made. So there's some really beautiful experiments where they show impact of drops of different viscosities, and they're able to recover the dynamics of the air film. Here you see measured in nanometers as a function of time and obviously space, and look at how these drops contact and all the different modes of contact which they see. So all of these drops rebound, I believe. So these are the different kind of modes which they mentioned. So I mentioned the film and the kink. They also see this dimple mode. So here you see their experiments. This is the prediction of our model, which I just showed you, and their experiment sees the transition here. So that first glance, that looks like a bit of a disaster, but the difference is that they're not contacting a solid surface, they're contacting an oil film. So clearly there'll be some difference due to the presence of this oil film. And what will be interesting now is to see if we can predict this transition with the same model, or with a kind of generalized model. Okay, so going back in time, the kind of first work we did in this area was to look at kinetic effects in dynamic wetting. And the question you want to answer there is how fast liquids can spread over a solid. So going back to this drop splashing phenomenon, there's a very nice paper in 2015 which suggests strongly that the splash is generated due to the presence of, due to essentially to the wetting process. So what they did is they drilled holes in the substrate to reduce the gas pressure in different areas. So if they reduce it in the center, the drop still splashes, as you see here. But if they reduce it on the outside, this kind of wetting mechanism, then they're able to suppress the splash. And so there's strong evidence that it's this wetting process which is really key to splashing. And if we look at a relatively recent annual review, they also conclude that air skating under the center of the drop is irrelevant for the splashing transition. Okay, so let's talk about why wetting is important for splashing. So essentially, the picture we have is that at certain speeds, a lamella is driven out. And then the question is, if this is going too fast, essentially it can no longer displace the gas. It takes off from the surface and it generates a splash. And this is the idea in the model, which is kind of the most advanced model of splashing developed by Rabiu and Gordillo. And so if we think about this in its simplest case, what it means is if we have a liquid spreading over a solid, when we go too fast, then suddenly the liquid can no longer displace the air, and air becomes entrained underneath the droplet, or the lamella in this case. So if we turn this picture on its side, actually what we can see is something that looks a lot like a different process, and that is the process of dip coating. So dip coating is the process where you simply drive a solid through a liquid bath at some continuous speed. And what you want to see is above some critical speed, do you entrain air, and how can you avoid that air entrainment? So what's nice about this process is there are also a lot of experiments on this, and it's a steady process without a lot of the complexities of drop impact. So the idea we're going to pursue is to think about there being a maximum speed of wetting at which liquids can displace the gas, and that it's the same mechanism in drop impact and coating processes. So by studying this one, we should get some insight into this process. So what does it look like when you go above this maximum speed? Well, this will show a plate being plunged into a liquid bath too fast, if you like, hopefully. Okay, and what you'll see is that a film is entrained into the liquid bath. That film becomes unstable and it breaks up into gas bubbles. Okay, and by measuring the volume of the gas bubbles, you can actually see that this film has width a few microns, and so it starts to become comparable to the mean free path in the gas. So what we developed is a computational framework, again based on finite elements, which is similar to some previous works by Satish Kumar in Minnesota on coating flow simulation, but now we incorporate gas kinetic effects in the same way as I showed you before, except for it's now a bit simpler because this is a steady problem. So what do we see? Well, if we think about a wettable solid being located here, then we predict that at low speeds or low capillary numbers based on the speed of the plate, the liquid just bends up to meet this plate. As we ramp up the speed, we start to drive this interface further and further down into the tank until eventually there are no more steady state solutions. And that gives us our maximum speed of wetting. And that's all we're really interested in here. So what does the flow look like here? Well, what you see is the liquid gets pulled down because the solid is moving down. The liquid pulls gas down the free surface. The solid pulls gas down the solid surface. And this is a steady state problem. So the gas has to go somewhere and it's ejected through the center. So the reason we picked this is that this dip coating has been done in a vacuum chamber. And it's been shown quite clearly that as you reduce the ambient pressure, you increase the speed at which you can coat. So you increase the maximum speed at which liquids can wet solids. And what we see, what's kind of obvious, is that if we use the conventional model, there's no link between the pressure and the model. But if we use the model with gas kinetic effects in, there is a link and the trend looks about right. So why does this happen? Well, again, it's the idea that for kind of Stokes flow with no slip, it's very hard to remove gas from thin gaps. And with gas kinetic effects, because of this reduced effective viscosity, it's much easier. So with the lower effective viscosity, you build lower pressure gradients, as you can see here, and therefore you can coat faster, or you can go faster. Okay, so I started by kind of motivating all this through splashing. What are the implications for splashing? Well, in this paper by Xu and partners, they look at a threshold pressure. And when you're above that threshold pressure, you splash. And when you're below it, you spread. And what's nice is they did this, this experiment for a number of different gases and looked at this threshold pressure as a function of velocity, impact speed. Now, all I'm going to do is see whether, if indeed Knudsen effects are the important thing here, whether we can collapse this onto dimensionless coordinates. And so the idea is to plot in terms of Knudsen number, a threshold Knudsen number, if you like, which depends on threshold pressure and the molecular weight of the gases. We can essentially non-dimensionalize these molecular weights with respect to air. And if we do that, we find this collapse of data. So in a sense, I've done nothing. There's no theory, no new modeling here. It's just indicative that the same effects are at play here as in coating. So what's nice is that, again, a couple of months ago, there was a new article looking at a different angle. So I've talked about reducing the atmospheric pressure to increase the Knudsen number. The other possibility is that you decrease the length scale. And so what they've done is they've taken impact on millimeter-sized drops, which is very popular, but they've also looked at micro drops. And so what they see is that even at larger Weber numbers, which is kind of the dimensionless impact speed, you don't splash with smaller drops. And the reason is that the characteristic scales here of the lamella become close to the mean free path in the gas. So again, there's interesting work to be done here. Okay, so those were the kind of isothermal processes I said I would talk about. This is now the looking at suspending drops through evaporation, and this is the work which Indrajit Chakraborty has led. And what we're going to do is look at the quasi-static Leidenfrost effect. So that's the effect where a drop sits on a solid in a quasi-static state, so it is evaporating but relatively slowly. And so we can look, or experimentalists can look and measure the properties of the vapor film in this state. And what we'd like to do is see if our computational model can be extended to capture essentially the geometry of these drops. So first of all, these are much thicker, so gas kinetic effects are negligible, at least for the time being. And now we need to think about the fact that we have a hot wall, we have a liquid which is at the boiling temperature, and we have this evaporation as a result. And what we see from all that is that we have an additional term in our model, which has all the things you might expect to see, like the latent heat. We see the difference in temperature between the wall and the liquid, and various other properties. And what we can do, this is a dynamic model, so we can evolve towards the equilibrium state. We can run the dynamics, if you like. Now, the most popular model in the literature so far for these quasi-static drops is a model developed by Sobak. And what he considers is just straight for the equilibrium state, so that you can consider equilibrium in the drop. So you have the balance of pressure, hydrostatic pressure, and capillary forces. And you knock out all time dependencies, you ignore the flow within the drop, because the drop is much more viscous than the gas. And the result is that you get an even simpler model for the evolution of this film, or for the shape of this film, I should say. So now you couple that, you patch this essentially together with the usual Young-Laplace equation for the top of the drop, and that gives you a shape of the whole thing. So what we'd like to do is compare our model to Sobak's and see how they capture experiments. And the basic conclusion is that both of these describe experiments very nicely. And in particular, they're able to describe lots of new effects which haven't been seen experimentally, like, for example, dimple-less drops, which you see at very small radii, where you have no change in sign of curvature as you go around the vapor layer. And also this remarkable effect that for small drops, instead of getting closer and closer to the substrate, they actually take off. What's remarkable, kind of interesting, is that for large drops, the Sobak model agrees with the experiments, but our computations diverge. And that's because what we see is if we neglect interior flow like Sobak, we see this puddle-like shape, which they see in the experiments. But if we put the correct viscosity in particular of water, we see this strong flow being driven within the drop, and that changes the shape of the drop to this much more upright shape compared to what we see in experiments. And similarly, we see a different vapor film. So here in experiments and in Sobak, you see this pocket, this dimple. And for our simulations, we see this so-called wimple shape where we have this kind of W being formed. So that's kind of interesting and annoying all at once. But what it seems is likely is that our assumption of axisymmetry goes out the window for these large drops. And if we look at recent articles, you can see in these Leidenfrost drops, these appearance of cells, this clear breaking of axisymmetry, and the need for fully 3D models to capture these kinds of flows. So what's nice, as I mentioned, is we can capture dynamics. The most interesting dynamical effect is the so-called chimney instability, where for sufficiently large drops, the vapor essentially punctures through the top of the drop. And we can see that in our simulation. So we start with a drop, we deposit it, it forms a puddle, and then this chimney instability kicks in, and this is the kind of shape we see just before the puncture. Okay, so I think I'm on time. I just want to mention a couple of kind of current or future directions. Firstly, we're doing some experiments in Warwick looking at the impact of solid spheres at reduced pressure on tanks of liquid. And so what you see here is two impacts, one at reduced ambient pressure, and you see very different dynamics. Notably, you see a cavity forming here and being suppressed at reduced pressures. And it seems like the mechanism is very different from the ones I've been talking about, because the collapse here is based on density, not on ambient gas pressure. And so here you see the line between cavity and no cavity. And if we'd done the same thing with gas pressure, this wouldn't collapse as well. There's also obviously the extension of the Leidenfrost towards dynamic cases. So in particular, the impact of drops, where there are experiments, for example, in Shirota 2016. And what you see there is at lower speeds, you get this kind of complex boiling underneath the drop. And at higher, at low temperatures, you get this. And at higher temperatures, you see Leidenfrost films being generated and no contact and no heat transfer. So the final one is just a kind of fun one, which we started working on during one of the lockdowns, I think. And this is with Anton, who's in Bath. And these are some experiments which were published in Nature a few years ago, where they looked at hydrogel spheres on hot solids. And well, let me just show you essentially what happens. So when you deposit these hydrogel spheres on a hot surface, which is just a frying pan here, essentially, what you see is that they bounce, and that in particular, the bouncing is sustained by the Leidenfrost effect. Okay, so clearly, if there was no Leidenfrost effect, these drops would eventually come to rest, but somehow there is power being put into these by the Leidenfrost mechanism. So there are experiments showing how that works. If we look at a cold substrate, just a normal hydrogel sphere impacts and rebounds with slightly less kinetic energy. But if we take a hot substrate, we see remarkably complex dynamics where we have this vapor film which oscillates before it rebounds, and energy is injected into the drop to sustain this bouncing. Now, hydrogel spheres is just essentially a posh name for what's called water balls or water beads. So in one of the desperate moments with my children during lockdown, to entertain them, I bought some of these spheres. Here they are. So they start off tiny, and then they absorb so much water that they're essentially 99% water once full. And if this is an experiment that I can do, I'm sure it's an experiment you can all do. You can just put them on a frying pan and watch them bounce around for fun, and that will entertain children for at least 2 or 3 minutes. Okay, so that's the end. Thank you all for listening. I'll happily take any of your questions. It's a rather old pre-social distancing photo of our group in Warwick. Some thanks to the various funders, and thank you for listening.